Look up at the night sky. Every star, every galaxy, every glimmer of light you can see is part of an almost unimaginably vast cosmic tapestry. But what if I told you that everything your eyes can perceive, everything telescopes can detect, every planet, every sun, every swirling nebula amounts to less than 5% of what's actually out there? The universe we think we know, the one painted in light, is merely the faintest shimmer on the surface of a far deeper, far darker, and almost entirely invisible ocean. For decades, astronomers have been piecing together a staggering truth. The cosmos is dominated by two profound and elusive phenomena, dark matter and dark energy. These are not just empty names for things we don't understand. They are the hidden architects of reality itself, holding the ultimate keys to the universe's past, present, and future. They dictate the very fate of everything that exists, and yet they remain the greatest unsolved mysteries in all of science. This revelation is like discovering that the world you live in is just the furniture in a house whose walls, floors, and foundation are made of materials you cannot see or touch. It fundamentally challenges our place in the cosmos and forces us to question the very nature of reality. The hunt to understand these dark components is more than a scientific pursuit. It's a journey to the absolute frontiers of human knowledge, a quest to uncover the hidden rules that govern existence. It's a story written in the empty spaces between the stars, in the subtle tug of gravity where nothing seems to be, and in the baffling acceleration of the universe's expansion. In this video, we are going to embark on that journey together. We will explore 25 mind-blowing facts about dark matter and dark energy, each one a piece of this incredible cosmic puzzle. From the ghostly gravitational fingerprints of dark matter in colossal collisions of galaxies to the repulsive force of dark energy that is tearing the very fabric of space apart, we will dive into the evidence, the theories, and the breathtaking implications of what it means to live in a universe where the vast majority of everything is, and may forever remain, hidden in plain sight. Prepare to have everything you thought you knew about the cosmos challenged, as we venture into the deepest dark to uncover the secrets of the universe's true nature. So let's begin with a fact that redefines our entire perspective, the foundational truth that makes this entire investigation necessary. The universe, for all its splendor and scale, is mostly invisible. When we add up everything we can possibly detect, every galaxy, every star, every cloud of gas and speck of dust, it amounts to a mere 5% of the total content of the cosmos. Think about that for a moment. Every single thing that science has ever studied directly, from the smallest bacterium to the largest supercluster of galaxies, represents just a tiny fraction of what is actually out there. This normal matter, the stuff made of protons, neutrons, and electrons that forms the periodic table and everything we've ever touched, is known as baryonic matter. And it is profoundly in the minority. The remaining 95% is the dark sector. About 27% of the universe is composed of dark matter, an invisible substance that does not emit, absorb, or reflect light, yet whose gravitational pull is absolutely essential for holding galaxies together. Then, dominating everything is dark energy, accounting for a staggering 68% of the universe. This is not matter at all, but a mysterious form of energy inherent to the fabric of space itself, and it's causing the expansion of the universe to accelerate. To truly grasp the scale of our ignorance, consider a simple analogy. Imagine you are standing on a beach looking out at the ocean. You see the white foam on the crest of the waves, the occasional piece of seaweed floating by, maybe a fish jumping. That visible activity, that familiar world of water and life, is like the 5% of normal matter. It's what we can easily perceive, but beneath the surface lies an immense, deep, and dark ocean, an environment of colossal weight and mystery. That deep ocean represents the 27% of dark matter. Its invisible presence dictates the movement of the waves and currents on the surface, even though we can't see it directly. And then, expanding this thought further, the dark energy is like the incomprehensible volume of the ocean's water itself, a force so dominant that it is actively pushing the entire shoreline, the very horizon, away from you at an ever-increasing rate. We are, in a very real sense, just studying the foam on a cosmic ocean whose true depth and nature remain almost entirely unknown to us. This isn't a small gap in our knowledge, it's a chasm, revealing that the reality we experience is just a glimmer on the surface of a much darker, far more mysterious universe. This realization that we are blind to most of the universe naturally leads to a critical question. If we can't see dark matter, how do we even know it's there? The answer lies in observing its ghostly grip on the cosmos, a gravitational signature first detected nearly a century ago. Our story takes us back to the 1930s, to a brilliant and often controversial astronomer named Fritz Zwicky. Zwicky was studying the Coma Cluster, a vast collection of over 1,000 galaxies bound together by gravity, millions of light years across. He measured how fast these individual galaxies were orbiting the cluster's center. According to the well-established laws of gravity, their speed should be determined by the total mass of the cluster, the combined gravitational pull of all the stars, gas, and dust that telescopes could see. But Zwicky's calculations revealed something astonishing. The galaxies were moving at velocities far too high to be explained by the visible mass alone. They were whizzing around so quickly that the gravitational pull from the observable matter should have been completely insufficient to hold the cluster together. The entire system should have flown apart eons ago, yet there it was, a stable, gravitationally bound structure. Zwicky concluded that there must be a huge amount of unseen matter providing the extra gravitational glue, an invisible scaffold holding the cosmic city together. He called this missing material Dunkel Materie, which translates directly to dark matter. This missing mass problem that Zwicky identified in galaxy clusters is in fact a universal phenomenon, and we see its effects on a smaller, more intimate scale right within individual galaxies like our own Milky Way. Think of our solar system. The planets orbit the Sun, and their speeds are governed by the Sun's immense mass. The closer a planet is to the Sun, the stronger the gravitational pull, and the faster it needs to travel to maintain its orbit. Mercury moves much faster than Neptune. This is a fundamental rule. However, when astronomers measured the orbital speeds of stars and gas clouds on the outskirts of spiral galaxies, they found something that completely defied this logic. Instead of slowing down as you move farther from the galactic center, as you would expect if most of the mass were concentrated in the bright core, the orbital speeds remain constant. These stars on the outer edges are moving just as fast as those closer in. It's as if every car on a highway, regardless of whether it's near the city center or far out in the countryside, was traveling at the exact same high speed. The only way this makes sense is if the galaxy is embedded within a massive, invisible sphere of matter, a halo of dark matter that extends far beyond the visible edge of the galaxy. This halo provides the extra gravitational pull to keep those high-speed outer stars from being flung off into intergalactic space. Without this dark matter anchor, galaxies like our own would simply unravel, their stars scattering into the cosmic void. So, while we cannot see dark matter directly, its gravitational influence is undeniable, a silent force shaping the architecture of the universe on the grandest scales. While Fritz Zwicky's work on galaxy clusters was groundbreaking, it was often met with skepticism, seen by some as an anomaly or a problem with our understanding of gravity on the largest scales. The true turning point, the evidence that cemented dark matter as a fundamental component of the universe, came decades later from observations much closer to home, inside the serene, spinning disks of spiral galaxies like our own. In the 1970s, astronomer Vera Rubin, along with her colleague Kent Ford, turned their attention to these familiar cosmic pinwheels, using sophisticated instruments to measure the velocities of stars and gas clouds at different distances from the galactic centers. They were expecting to confirm a pattern as old as Kepler's laws of planetary motion. Just as planets orbit the Sun, with Mercury speeding along and Pluto drifting slowly, stars in a galaxy should follow a predictable speed pattern. The vast majority of a galaxy's visible mass, its brilliant core and sprawling arms of stars, is concentrated toward the center. Logic dictates that a star orbiting far out on the edge, where the gravitational pull from that central mass is much weaker, should be moving significantly slower than a star orbiting close in. What Rubin and Ford discovered, however, was anything but logical. Their data revealed a flat rotation curve. This means that as they measured stars farther and farther from the galactic center, their orbital speeds did not drop off as expected. Instead, the speeds remained remarkably constant. A star tens of thousands of light years from the core was hurtling through space at roughly the same velocity as a star near the inner regions. It was a result that defied the established laws of physics as applied to the visible universe. Imagine a giant merry-go-round where children sitting near the center are spinning at the same tremendous speed as those clinging to the very outer edge. Without some unseen mechanism at work, those on the outside would be flung off immediately. That is precisely the situation within spiral galaxies. The visible matter alone simply does not provide enough gravitational force to keep these high-speed outer stars in their orbits. The galaxy should have torn itself apart long ago. The only plausible explanation is that each galaxy is swaddled in an enormous, invisible halo of matter, a halo that extends far beyond the visible edge of the stars. This halo provides the additional gravitational pull needed to account for the constant orbital speeds. The dark matter isn't concentrated in the disk where the stars are. It forms a vast, diffuse sphere that envelops the entire luminous galaxy. Vera Rubin's meticulous work provided the most direct and compelling evidence that this mysterious substance was not just a feature of rare, dense galaxy clusters, but a universal and essential ingredient in every galaxy. Her findings transformed dark matter from a curious anomaly into a central pillar of modern astrophysics, forcing us to accept that what we see in the night sky is only a small part of the cosmic story, with the true bulk of a galaxy's mass remaining shrouded in darkness. But the influence of dark matter extends far beyond just holding individual galaxies together. It is, in fact, the master architect of the entire cosmic landscape. To understand this, we need to journey back to the very beginning, to the hot, dense soup of particles that filled the universe moments after the Big Bang. In that primordial chaos, there was a crucial difference between normal matter and dark matter. Normal matter, the protons, electrons, and neutrons that would eventually become us, was constantly buffeted by intense radiation pressure. Light photons pushed and shoved these particles, preventing them from easily clumping together. It was like trying to build a sandcastle in a stormy sea. The waves kept washing the sand away. Dark matter, on the other hand, is thought to be non-baryonic, meaning it does not interact with light or radiation in any way. It was completely oblivious to this photon barrage. While normal matter was being scattered, dark matter was free to start gathering under its own gravity. This gave dark matter a monumental head start. Tiny, random fluctuations in the density of the dark matter universe began to amplify. Slightly denser regions had slightly stronger gravity, which pulled in more dark matter from the surroundings, making them even denser. Over hundreds of millions of years, these invisible concentrations of dark matter grew into an immense web-like scaffolding that stretched across the entire cosmos. They formed vast gravitational wells, cosmic potholes in the fabric of space-time. Only after the universe had expanded and cooled enough for radiation pressure to weaken could normal matter finally respond to gravity's call. The atoms and gas were drawn inexorably into these pre-existing dark matter wells. It was within these gravitational basins that the first stars could ignite, the first galaxies could coalesce, and the magnificent large-scale structure of the universe could take shape. This is why the cosmos isn't just a smooth, uniform soup of galaxies. Instead, telescopes reveal a breathtaking cosmic web. Long, thin filaments of millions of galaxies connecting at dense nodes where enormous galaxy clusters reside, all separated by vast, empty voids. What we are seeing is the luminous trace of the underlying dark matter skeleton. The galaxies are like glitter sprinkled onto sticky spider webs, outlining a structure that is itself invisible. Without dark matter's initial gravitational blueprint, the universe would be a far more boring and homogeneous place. The formation of galaxies would have been a much slower, more scattered process, and the intricate, interconnected architecture that defines our universe simply wouldn't exist. Dark matter didn't just help build the universe, it drew up the blueprints and laid the foundation for everything we can see. But if dark matter's primary role is as a cosmic architect, providing the gravitational scaffolding for the universe, how can we be so sure it's a real substance and not just a flaw in our understanding of gravity? For decades, this was the central debate. Then, in 2006, astronomers witnessed an event in deep space that many consider the most compelling direct evidence for dark matter's existence: the collision of two galaxy clusters known as the Bullet Cluster. This was not a gentle merging, but a cosmic car crash of unimaginable scale, offering a perfect natural experiment. Think of it like this: if you wanted to prove that the wind exists even though you can't see it, you could watch what happens to leaves and dust in the air during a storm. The Bullet Cluster gave us a storm on a cosmic scale, allowing us to see how different types of stuff behave when forced apart. In this colossal collision, the most abundant component of the cluster's enormous clouds of superheated gas slammed into one another. This gas is normal baryonic matter, and because it's made of charged particles, it interacts strongly through electromagnetic forces. Just like two clouds of smoke colliding, this gas got tangled up, slowed down, and piled up in the center of the merger. This pile-up of hot gas is so energetic it glows brightly in X-rays, which telescopes like the Chandra X-ray Observatory can detect. So, if all the matter in these clusters were normal, visible matter, the vast majority of the mass should be concentrated right there in the center where the gas is. However, astronomers used a different technique called gravitational lensing to map the true distribution of mass. Einstein's theory of general relativity tells us that mass warps the fabric of space-time, bending the path of light passing near it. By carefully analyzing how the light from distant galaxies behind the Bullet Cluster was distorted, they could create a map of the total mass, both visible and invisible, in the region. The result was startling. The map revealed that the bulk of the mass was not in the center with the clumped-up gas. Instead, it had sailed right through the collision zone and was now located in two distinct lobes on either side of the central gas cloud. This mass had behaved like a ghost, completely unaffected by the electromagnetic smash-up that had slowed the normal matter. This separation is the smoking gun. The stuff that makes up most of the mass clearly interacts only, or almost only, through gravity. It does not interact with light or with itself in the way normal matter does. This observation deals a heavy blow to alternative theories that try to explain away dark matter by modifying the laws of gravity. If modified gravity were the answer, the apparent mass should have stayed with the visible matter, the gas. But it didn't. The Bullet Cluster demonstrates that there is a separate, collisionless component to the universe, a substance that vastly outweighs everything we can see. It's as if we watched two crowds of people walk through each other, but the crowds were mostly made of ghosts that passed through without a bump, while only their visible backpacks, the normal matter, got caught in the middle and collided. This single observation powerfully confirms that dark matter is not just a theoretical figment. It is a physical reality, a dominant component of the cosmos that moves through the universe we know like a shadow. Of course, with such compelling evidence from cosmic collisions like the Bullet Cluster, we can be confident that dark matter is a real physical substance. But this immediately raises one of the most fundamental and frustrating questions in all of modern physics. What exactly is it made of? We've spent decades observing its gravitational effects, mapping its cosmic web, and confirming its existence, yet its true identity remains one of science's great secrets. The most productive way to approach this mystery is to first rule out what it cannot be, to clear away the more familiar candidates that might initially come to mind. First and foremost, dark matter is not simply made of black holes. While it's a captivating idea that the universe's missing mass is locked away in countless invisible cosmic traps, the evidence doesn't support this as the primary solution. We know that stellar mass black holes, the remnants of massive stars, cannot account for the sheer amount of dark matter needed. There just aren't enough of them. The more intriguing possibility involves so-called primordial black holes, hypothetical objects that could have formed from ultra-dense regions in the very first moments after the Big Bang. These could range in size from a mountain to a star. However, detailed searches, for instance by monitoring the way they subtly distort the light of distant stars through gravitational microlensing, have placed severe limits on their numbers. While a small fraction of dark matter could potentially be made of these ancient relics, they are highly unlikely to be the main component. Another common guess is that dark matter is antimatter. After all, antimatter is real. We can create it in particle accelerators. Particles of antimatter have the same mass as their normal matter counterparts but opposite charge. The problem is, when matter and antimatter meet, they annihilate each other in a spectacular flash of energy. If vast clouds of antimatter were floating around in the halos of galaxies, we would expect to see a constant, diffuse glow of gamma-ray radiation from these annihilation events at the boundaries where they interact with normal matter. Our telescopes have searched for this telltale signal and have not found it in the amounts required. Dark matter, whatever it is, appears to be remarkably stable and does not annihilate with the matter we are made of in any significant way. Could it be something more mundane, like clouds of normal gas that are simply too cold or dark to see? This is also ruled out. If dark matter were made of ordinary baryonic particles, protons and neutrons in the form of cold, diffuse gas or failed stars known as brown dwarfs, it would still interact with light. It would absorb or block the light from sources behind it, or it would be detectable by its subtle emission in infrared wavelengths. Extensive surveys have scanned the skies for these massive astrophysical compact halo objects, and they've found that while such objects exist, they are far too few to explain the gravitational effects we observe. The overwhelming majority of dark matter must be something entirely different from the atoms that make up our world. This series of dead ends leads some to question the initial premise itself. Perhaps we don't need a new type of matter at all. Maybe our understanding of gravity, as described by Einstein's theory of general relativity, is simply incomplete or incorrect on the vast scales of galaxies and galaxy clusters. This idea is the basis of theories like MUND, which stands for Modified Newtonian Dynamics. MUND proposes that gravity behaves differently when it becomes incredibly weak, such as at the edges of galaxies, creating the illusion of extra mass without any actual matter being there. It's an elegant idea that successfully explains the flat rotation curves of individual galaxies. However, it runs into profound difficulties when faced with the evidence from cosmic collisions like the Bullet Cluster. As we saw, the gravitational mass and the normal matter were clearly separated. MUND, in its basic form, would predict that the gravity should follow the visible matter, the gas which it demonstrably does not. While researchers continue to develop more complex relativistic versions of MUND, these theories struggle to explain the full suite of cosmological data, from the cosmic microwave background to the formation of large-scale structure as elegantly as the dark matter model does. So, by process of elimination, we are left with a staggering conclusion. Dark matter is almost certainly an entirely new, exotic form of matter that does not participate in the electromagnetic or strong nuclear forces. It feels gravity and it may interact through the weak nuclear force, but otherwise it is largely oblivious to the universe of light and atoms that we inhabit. It is a ghostly substance streaming through our planet, our homes, and even our bodies without a trace. This realization shifts the search from the vastness of space to the subatomic realm, where physicists are now hunting for the hypothetical particle that could be the fundamental building block of the cosmic shadow. So, if dark matter is this new, exotic particle, what could it possibly be? After decades of theoretical work and experimental searches, one candidate has risen to the forefront, a hypothetical particle that strikes such an elegant balance between theory and observation that it's often described as a miracle. This candidate is known as a WIMP, which stands for Weakly Interacting Massive Particle. The name itself tells you its two most important properties. First, it's massive, meaning it has a significant weight, perhaps tens or hundreds of times heavier than a proton. Second, and most crucially, it is weakly interacting. This means it does not feel the electromagnetic or strong nuclear forces, but it might interact through the weak nuclear force, the same force responsible for certain types of radioactive decay. This incredibly feeble interaction is precisely why WIMP are so difficult to detect. They pass through normal matter as if it weren't even there. The reason WIMP are so compelling, however, goes far beyond just a clever name. It lies in a beautiful piece of cosmic coincidence often called the WIMP miracle. Here's how it works. In the searing heat of the very early universe, just after the Big Bang, a soup of every conceivable type of particle would have been constantly colliding and annihilating with their antiparticles, creating a frenzied, energetic chaos. WIMP would have been part of this frenzy, but as the universe expanded and cooled in those first fractions of a second, the average energy of the particle soup dropped. There eventually came a point where the energy was too low to create new WIMP pairs from the collisions of other particles. At this moment, the frenetic dance of creation and annihilation stopped. The remaining WIMP, which could no longer find partners to annihilate with, were effectively frozen out of the thermal bath. They became stable relics drifting through the expanding cosmos. Now, the truly miraculous part. When physicists calculate the expected density of these frozen-out WIMP based on nothing more than their estimated mass and interaction strength, parameters that emerge naturally from theoretical frameworks like supersymmetry, the result is astonishing. The calculated abundance aligns almost perfectly with the amount of dark matter we observe in the universe today. It's as if the universe left us a clue written in the fundamental laws of physics. The fact that a simple, elegant thermal relic process predicts the exact right amount of dark matter is a powerful argument that we might be on the right track. It suggests that dark matter isn't some bizarre, ad hoc invention, but a natural and inevitable consequence of the physics of the early universe. This tantalizing possibility has sparked a global, multi-decade hunt to capture a WIMP in the act. Because these particles are so elusive, detecting them requires extraordinary measures. The primary strategy is known as direct detection, and it involves building incredibly sensitive experiments deep underground. Why underground? To shield the detectors from the constant barrage of cosmic rays and other background radiation that would completely swamp the faint signal of a potential WIMP interaction. These laboratories, housed in former mines or deep beneath mountains, are some of the quietest places on Earth. The detectors themselves are technological marvels, often consisting of large vats of ultra-pure liquid xenon or germanium crystals, chilled to extremely low temperatures. The idea is to wait patiently for the once in a blue moon event where a WIMP, streaming through the Earth as part of the galactic dark matter halo, might actually bump into the nucleus of an atom in the detector. This collision would be incredibly subtle, imparting only a tiny amount of energy, a minuscule flash of light or a small charge, that the hypersensitive instruments are designed to pick up. Experiments like LUX Zeppelin in the United States, Xeno NNT in Italy, and Panda X in China are constantly pushing the boundaries of sensitivity, creating ever more pristine environments to listen for the faintest whisper of a WIMP. So far, despite their incredible efforts, no definitive, unambiguous signal has been found. Each null result is still valuable, as it rules out vast swaths of possible masses and interaction strength, gradually narrowing the search and forcing physicists to consider even more exotic possibilities. The hunt for WIMP is a testament to human ingenuity, a patient, meticulous quest to make contact with the hidden majority of our universe. Yet the persistent silence from deep underground detectors highlights a critical reality in science. We must always keep our minds open to other possibilities. While WIMP remain a compelling candidate, the universe has a habit of surprising us, and the hunt for dark matter has inspired a zoo of other theoretical particles, each with its own unique appeal. One of the most fascinating alternatives is the action. Unlike the heavy WIMP, the action is imagined to be incredibly light, billions or even trillions of times less massive than a proton. What's remarkable is that the action wasn't originally invented to solve the dark matter puzzle at all. It was proposed to resolve a deep and perplexing mystery in the standard model of particle physics known as the strong CP problem, which concerns why the strong nuclear force behaves so symmetrically. The fact that a particle proposed for one fundamental reason could also, almost by accident, account for the missing mass of the universe is a beautiful example of cosmic economy. If actions exist, they would have been produced in vast quantities in the early universe, not through a thermal freeze out like WIMP, but through a mechanism akin to cosmic crystallization. Their collective behavior would be less like a stream of individual particles and more like a pervasive, invisible field of energy oscillating throughout space. Because they are so light, vast numbers of them would be needed to account for dark matter, meaning that trillions of actions could be passing through your hand every second without you ever noticing. The search for them is just as ingenious as the WIMP hunt, but uses entirely different technology, often involving powerful magnetic fields inside resonant cavities designed to convert a passing action into a faint but detectable microwave photon. Beyond actions, theorists have explored a whole spectrum of other ideas. Consider the sterile neutrino. We know that regular neutrinos are ghostly particles that barely interact with matter, but they are still a part of the standard model. A sterile neutrino would be a hypothetical heavier cousin that doesn't even interact via the weak force, making it even more elusive. If they exist, they could decay, producing faint X-ray signals that astronomers are actively searching for in galaxy clusters. Then there are SIMP, or strongly interacting massive particles. As the name suggests, this candidate turns the WIMP idea on its head. What if dark matter particles do interact with each other quite strongly through a new, unknown force while still ignoring normal matter? This self-interaction could solve some small-scale puzzles in galaxy formation, like why the centers of dark matter halos appear less dense than some simulations predict. It's as if the dark matter particles can bump into each other, smoothing out their distribution. This incredible diversity of candidates, from heavy WIMP to wispy actions, from decaying neutrinos to self-interacting SIMP, isn't a sign of confusion, but a testament to the creativity of scientists faced with one of nature's greatest riddles. It shows that the solution might be something we haven't even dreamed of yet. Each proposed particle leads to a different experimental approach, a different way of listening to the cosmos. This multifaceted hunt ensures that we are not putting all our eggs in one basket, but are exploring every conceivable avenue to illuminate the dark. This search for the constituent particle of dark matter is perhaps the most ambitious and technologically demanding experiment in the history of science. It hinges on a breathtakingly difficult goal: to directly detect a single, fleeting interaction between a particle of dark matter and a particle of the ordinary world. To appreciate the scale of this challenge, you have to understand just how ghostly these WIMP are predicted to be. Trillions of them are thought to be streaming through your body every single second, moving at speeds comparable to a meteorite entering our atmosphere. Yet, their interaction is so incredibly weak that over the course of your entire lifetime, the cumulative effect of all those trillions upon trillions of particles might result in, at most, 1 or 2 collisions with the nuclei of atoms in your body. We are trying to observe an event that is, for all practical purposes, non-existent in our daily experience. To have any hope of seeing such a rare event, scientists have had to create laboratories of unparalleled silence and purity. These are not facilities on mountaintops or in open fields. They are buried deep underground, shielded by a mile of solid rock. Places like the Sanford Underground Research Facility in South Dakota or the Gran Sasso Laboratory in Italy use the Earth itself as a giant cosmic ray shield. Cosmic rays, high-energy particles from space, constantly bombard our planet's surface, creating a background chatter that would completely drown out the faint whisper of a dark matter interaction. Descending into one of these labs is like entering a sensory deprivation chamber for particles. The goal is to eliminate every possible source of noise to listen for a signal that might occur just a handful of times per year in a detector the size of a small room. At the heart of this quest are instruments of exquisite sensitivity, like the LUX Zeppelin experiment in South Dakota and the Zeno NNT experiment in Italy. The core of these detectors is a multi-ton vessel filled with liquid xenon, a dense, noble gas that has been purified to an almost unimaginable degree. We are talking about levels of purity where a single stray atom of a contaminant like krypton would be like a single grain of sand in an Olympic-sized swimming pool. This xenon is kept at a temperature of around -100 degrees Celsius, and it serves a dual purpose. First, its high density means there are a vast number of atomic nuclei packed into the space, increasing the infinitesimally small chance that a passing WIMP might bump into one. Second, xenon is an excellent medium for revealing such a collision. The detection principle is a marvel of engineering. If a WIMP were to collide with the nucleus of a xenon atom, it would deliver a tiny, almost imperceptible kick. This interaction would produce 2 telltale signals: an immediate, faint flash of light called a scintillation signal, and a subsequent release of a few electrons. These electrons are then drifted upward by a powerful electric field applied across the liquid xenon, pulling them into a thin layer of xenon gas at the top of the vessel. There, in the gas, a stronger electric field causes the electrons to produce a second, brighter flash of light. By meticulously measuring the timing, the location, and the intensity of these 2 light signals, physicists can precisely reconstruct the energy and the position of the interaction within the tank. Crucially, they can also distinguish the signature of a nuclear recoil, the hoped-for WIMP bump, from the more common signatures of background radiation, like electrons bouncing off atoms. This is the ultimate needle in a haystack search. The entire apparatus is a trap set for a ghost, waiting for an event so rare that it pushes the limits of statistics and patience. The detectors run continuously, year after year, accumulating what physicists call exposure, the product of the detector's mass and its running time. Every day that passes without a definitive signal is not a failure. It is a data point that helps rule out a wider range of possible WIMP properties. The experiments have become so sensitive that they are now probing territories where, if WIMP of a certain mass and interaction strength existed, we should have started to see them. Their continued silence is itself a profound result, forcing theorists to refine their models and consider even more elusive possibilities. This patient, meticulous work, conducted in the profound quiet of the deep earth, represents a fundamental human drive to reach out and make contact with the unknown, to finally grasp the nature of the dark substance that holds our universe together. While the direct detection experiments listen patiently in the silence of deep underground laboratories, another arm of the hunt is scanning the skies, searching not for the dark matter particles themselves, but for the fiery aftermath of their destruction. This strategy, known as indirect detection, operates on a thrilling premise. What if dark matter is not completely stable? What if, on rare occasions, two dark matter particles can collide and annihilate each other, converting their mass directly into a burst of energy and a shower of familiar particles, as predicted by Einstein's famous equation? Or perhaps, what if individual dark matter particles slowly decay over astronomical timescales into something we can see? In either scenario, the result would be the same, an unexpected, telltale glow of radiation emanating from regions where dark matter is thought to be most densely concentrated. It's like trying to find a hidden animal not by spotting the animal itself, but by listening for its roar or looking for its tracks. The most promising signature to look for is gamma rays, the most energetic form of light in the universe. If two WIMP were to annihilate, the energy released could produce a cascade of particles and radiation, culminating in a sharp spike of gamma rays at a very specific energy, a fingerprint that would be incredibly difficult to explain by any known astrophysical process. The challenge, of course, is that the universe is already filled with gamma rays from more conventional sources, pulsars, supernova remnants, and materials swirling into supermassive black holes. The key is to know where to look and what pattern to search for. The ideal hunting grounds are places that are rich in dark matter but relatively poor in the usual astrophysical gamma ray factories. This has led scientists to focus on two primary locations: the serene, ancient dwarf spheroidal galaxies that orbit our Milky Way, and the tumultuous, dense center of our own galaxy. Dwarf galaxies are particularly compelling targets. These small, faint satellites of the Milky Way are fascinating objects in their own right, often containing very few stars but, according to gravitational measurements, enormous amounts of dark matter. They are essentially pristine dark matter halos with just a sprinkling of visible stars. Because they lack the violent astrophysical engines of larger galaxies, they are incredibly clean environments for the search. If a gamma-ray signal were detected coming from one of these dwarfs, it would be a very strong candidate for a dark matter annihilation signal. For over a decade, the Fermi Gamma-Ray Space Telescope, a powerful observatory orbiting Earth, has been meticulously mapping the entire gamma-ray sky. It has collected vast amounts of data from dozens of these dwarf galaxies, looking for any statistically significant excess of gamma rays at specific energies. While there have been a few intriguing hints, slight bumps in the data that cause a flutter of excitement in the astrophysics community, no definitive, unambiguous signal has yet emerged. The absence of a clear signal is once again a valuable result, placing stringent limits on how often dark matter particles can annihilate with one another. The galactic center is a much more complex but potentially more rewarding target. The region surrounding the supermassive black hole at the heart of the Milky Way is believed to harbor an incredibly dense concentration of dark matter, a peak in the gravitational landscape of our galaxy. The potential signal from annihilations here could be immensely bright. However, this area is also a blazing cacophony of gamma rays from other sources, making it extraordinarily difficult to disentangle a potential dark matter signal from the background noise. Interestingly, Fermi data from the galactic center has revealed a mysterious and diffuse glow of gamma rays extending outward from the core, an emission that is not fully explained by known objects. For a time, this galactic center excess was a hot topic of debate, with some researchers arguing its properties were consistent with what we might expect from annihilating dark matter. However, further analysis has suggested that it could also be explained by a large population of unresolved millisecond pulsars or other stellar remnants. This ambiguity highlights the painstaking work of indirect detection, distinguishing a potential whisper from dark matter from the cosmic crowd. Beyond gamma rays, physicists are also searching for other indirect clues. They look for unusual fluxes of neutrinos, those ghostly particles that barely interact with anything, detected by enormous underground telescopes like IceCube at the South Pole. If dark matter particles were to get trapped and accumulate in the core of the Sun or Earth, their annihilations could produce a stream of high-energy neutrinos pointing back to their source. Similarly, instruments like the Alpha Magnetic Spectrometer on the International Space Station are precisely measuring the composition of cosmic rays, the high-energy particles that constantly bombard Earth. They are on the lookout for an unexpected overabundance of antimatter particles like positrons and antiprotons, which could be the debris from dark matter annihilations occurring throughout our galaxy. Each of these methods represents a different way of eavesdropping on the dark sector, a multi-pronged effort to catch dark matter in the act of revealing itself, not through its gravity, but through its potential to create a spark of light in the profound cosmic darkness. While underground labs listen for whispers and telescopes scan for distant glows, there is a third, radically different front in the hunt for dark matter. One that takes place not in the silence of deep space or the Earth, but within the controlled, violent chaos of the world's most powerful particle colliders. The most famous of these is, of course, the Large Hadron Collider, or LCH, a 27-kilometer-long ring buried beneath the border of France and Switzerland. You might remember it as the machine that discovered the Higgs boson, the particle that gives others their mass, but its mission extends far beyond that single, monumental achievement. The LHC is fundamentally a cosmic time machine, capable of recreating the conditions of the universe just a fraction of a second after the Big Bang, when energy densities were so immense that particles of a kind we never see today were popping into existence. The core idea behind this approach is beautifully simple. If we can't find dark matter out there in the cosmos, perhaps we can create it right here on Earth. The strategy hinges on one of Einstein's most famous insights, that energy and mass are two sides of the same coin. By smashing beams of protons together at velocities incredibly close to the speed of light, the LHC concentrates a staggering amount of energy into a vanishingly small point. This energy can then spontaneously transform into mass, creating new particles. In the vast majority of collisions, these particles are well known to physicists, things like quarks, electrons, and photons, all part of the Standard Model, our current rulebook for particle physics. But if dark matter particles do have some connection to our known universe, even an incredibly feeble one, there is a chance that these high-energy collisions could produce them. It would be like trying to understand an invisible ink by throwing two visible ink pots at each other with such force that the splash reveals the hidden substance. This is where the real challenge and the real ingenuity comes into play. Even if the LHC successfully creates a dark matter particle, that particle would be completely invisible to the massive, layered detectors like ATLAS and CMS that surround the collision points. It would simply fly through the detector's walls without leaving a trace, just as it flies through planets and people. So, if you can't see the particle itself, how do you prove it was ever there? The answer lies in a fundamental law of physics, the conservation of momentum. Think of it like a game of pool in a pitch-black room. If you see the cue ball moving toward a cluster of other balls and you hear a collision, and then you see several visible balls scatter away from the point of impact, you can deduce a lot about what happened. But if you notice that the visible balls are not flying away in a perfectly balanced pattern, and if their collective momentum seems to be skewed to one side, you would have to conclude that an invisible ball, one you cannot see, was also hit and carried away momentum in the opposite direction. This is precisely the signature physicists at the LHC are searching for. They look for proton-proton collisions where the debris of known particles, the things their detectors can see, exhibits a clear imbalance in momentum. Specifically, they measure the momentum perpendicular to the beamline, called the missing transverse momentum. If the visible particles all shoot out in one direction, with nothing detectable moving the opposite way to balance the books, it's a powerful indicator that something invisible and non-interacting carried the missing energy away. This something could very well be a dark matter particle. Of course, the universe is messy, and there are other ways to produce missing momentum, such as by creating neutrinos, which are also notoriously difficult to detect. So, the hunt involves incredibly complex statistical analyses, searching for an excess of these momentum, imbalanced events over and above what the standard model predicts should happen from known processes. It's a meticulous process of subtraction, looking for a ghost in the machine by carefully accounting for everything else. The ultimate hope is to not only produce dark matter, but to understand its properties by studying the pattern of the visible debris it leaves behind. The energy of the collision and the specific way the momentum is unbalanced could reveal the mass of the dark matter particle and even hint at how it might connect to the ordinary particles we know. The LHC represents the brute force approach to the mystery, an attempt to wrest the secrets of dark matter from the vacuum of space by recreating the primeval fire of creation itself. It's a bold and direct assault on one of nature's greatest puzzles, running in parallel with the patient waiting game of direct detection and the cosmic observation of indirect searches, each method complementing the others in our multi-pronged quest to illuminate the dark. Now, after focusing so intently on the gravitational glue of dark matter, we must turn our attention to an even more dominant and baffling force, one that operates in direct opposition to gravity and was only discovered through one of the most unexpected findings in the history of astronomy. For most of the 20th century, following Edwin Hubble's revelation that the universe is expanding, the central cosmic question was a simple one: how fast is that expansion slowing down? Everyone assumed that the collective gravitational pull of all the matter in the cosmos, stars, galaxies, and especially the unseen dark matter, must be acting as a brake on the universe's outward flight. The great debate was whether there was enough matter to eventually halt the expansion and pull everything back together in a big crunch, or if the universe would simply keep expanding forever, slowing to a near standstill over trillions of years. That was the paradigm. Then, in 1998, two independent teams of astronomers made a measurement that shattered this entire framework and fundamentally rewrote the story of the cosmos. These researchers weren't setting out to find a new force of nature. They were trying to measure the deceleration of the universe by using nature's most reliable cosmic yardsticks, type Ia supernova. These stellar explosions are incredibly valuable because they are standard candles. A type Ia supernova occurs in a binary star system where a dense white dwarf siphons material from its companion. Once the dwarf reaches a very specific critical mass, about 1.4 times the mass of our Sun, it undergoes a runaway thermonuclear explosion. Because this trigger point is always the same, the intrinsic brightness of these supernovae is virtually identical. This means that if you spot one in a distant galaxy, you can tell how far away it is by how dim it appears. Furthermore, because light takes time to travel across the vastness of space, observing a supernova in a galaxy billions of light years away is like looking billions of years into the past. The two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were in a friendly race to find these distant supernova. They would scan the skies, and when a candidate appeared, they would immediately point the world's most powerful telescopes, like the Hubble Space Telescope and giant ground-based observatories, to measure its brightness and, crucially, its redshift. Redshift tells us how much the universe has stretched since the light left the supernova. By comparing the distance from brightness to the redshift from expansion for many supernovae at different distances, they could plot out the history of the universe's expansion rate. They expected to see that the more distant, ancient supernova would show that the expansion was faster in the past, confirming that the universe has been slowing down over time. But the data told a completely different story. The distant supernovae were significantly fainter than they should have been if the universe had been steadily decelerating. After meticulously checking and rechecking for potential errors like interstellar dust dimming the light or intrinsic differences in the supernova, the astronomers were forced to accept a stunning conclusion. The supernovae were fainter because they were farther away than anyone had predicted. The only way this could be true is if the expansion of the universe was not slowing down at all. In fact, it was speeding up. The universe's expansion is accelerating. It was as if you threw a ball into the air, and instead of slowing down and falling back to Earth, it shot away from you faster and faster into the sky, defying gravity itself. This discovery was so revolutionary and so counterintuitive that the teams were initially deeply skeptical of their own results. But both groups, working completely independently, arrived at the same shocking finding. The universe is not being pulled back together by gravity. It is being ripped apart by a mysterious, repulsive force. For this monumental discovery, the leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics in 2011. This revelation required a fundamental shift in our understanding of physics. To explain an accelerating expansion, cosmologists had to introduce a new component into the cosmic inventory, an energy that permeates the very fabric of empty space itself, and that exerts a negative pressure, effectively pushing the universe apart. This mysterious entity was given the name dark energy. Its effect is the complete opposite of dark matter. While dark matter's gravitational pull works to gather matter and slow the expansion, dark energy's repulsive push works to separate matter and speed the expansion up. The discovery meant that the fate of the universe was not going to be a gradual slowing or a dramatic collapse, but an ever-accelerating runaway expansion that will ultimately lead to a cold, dark, and isolated future. The finding was not just a minor adjustment, it was a paradigm shift that revealed a universe dominated by a force we are only beginning to comprehend. The discovery that the universe's expansion is accelerating was a shock that demanded an explanation, and incredibly, the most promising candidate was an idea that Albert Einstein had proposed and then famously rejected 80 years earlier. This concept is known as the cosmological constant, often represented by the Greek letter lambda. The story begins in 1917 when Einstein was applying his new theory of general relativity to the universe as a whole. His equations beautifully described how matter and energy warp space-time, creating the force we experience as gravity. However, when he tried to model a stable, unchanging cosmos, he ran into a problem. The equations insisted that a universe filled with matter could not be static. The gravitational attraction of all that mass would inevitably cause it to either collapse in on itself or, under different conditions, to expand. But the scientific consensus at the time, based on the observations available, was that the universe was indeed eternal and unchanging. To force his equations to match this presumed static reality, Einstein introduced a mathematical fudge factor, the cosmological constant. This term represented a mysterious, repulsive force that would perfectly counterbalance the attractive force of gravity on the largest scales. Think of it as a kind of anti-gravity woven into the very fabric of empty space, a subtle pressure that pushed outward to prevent a cosmic collapse. With this constant carefully tuned, his model could describe a universe that was neither expanding nor contracting. Then, just over a decade later, Edwin Hubble's observations revealed that distant galaxies were in fact rushing away from us. The universe was not static at all, it was dynamically expanding, Upon learning this, Einstein reportedly declared the introduction of the cosmological constant his greatest blunder, an unnecessary complication that had caused him to miss predicting the expansion of the universe. For most of the 20th century, that's where the story ended. The cosmological constant was seen as a historical footnote, a cautionary tale about even the greatest minds sometimes clinging to incorrect assumptions. The expanding universe model, eventually leading to the Big Bang theory, became the standard, and the need for lambda seemed to vanish. But the discovery of the accelerating expansion in 1998 turned this entire narrative on its head. Astronomers realized that to explain why the expansion is speeding up, you need a term in the equations that acts exactly like Einstein's cosmological constant. The repulsive force he invented to hold the universe still was in fact the very thing needed to explain why it is flying apart faster and faster. What he considered his greatest blunder may well turn out to be one of his most profound insights. So, what is the cosmological constant in modern terms? Physicists now interpret it as the energy inherent to the vacuum of space itself. This is a deeply strange idea. We tend to think of a vacuum as true emptiness, a void completely devoid of energy. But quantum physics tells us that even at absolute zero, at the smallest possible scales, empty space is not empty at all. It is a seething, bubbling foam of virtual particles. Particle-antiparticle pairs constantly flicker into existence out of nothing, borrowing energy from the vacuum for an infinitesimally short time before annihilating each other and disappearing back into the void. This frenetic activity, confirmed by numerous experiments, endows every single cubic centimeter of empty space with a tiny, but non-zero energy density. This is the vacuum energy. When you add up this energy across the incomprehensible volume of the entire observable universe, the collective effect is a repulsive pressure, a constant, relentless push against the fabric of spacetime itself. This is what we call dark energy, and the cosmological constant is the simplest explanation for it. A fixed, unchanging energy density that causes the expansion of the universe to accelerate. The profound irony is almost too elegant to ignore. Einstein introduced lambda to achieve a static universe based on a flawed premise. He discarded it when the dynamic universe was discovered. And now we find that the universe is not just dynamic but accelerating, and his discarded constant provides the most straightforward explanation. It's as if the universe had the last laugh, revealing that his intuition, even when applied for the wrong reason, was pointing toward a fundamental truth about reality. Yet, this elegant solution comes with its own monumental puzzle, one that drives physicists to the brink of despair. When they try to calculate the predicted value of this vacuum energy using our best theories of quantum mechanics, the result is wrong by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst theoretical prediction in the entire history of science. This cosmological constant problem suggests that either our understanding of the quantum vacuum is drastically incomplete, or that the cosmological constant, while a compelling idea, is not the final answer to the dark energy mystery. This staggering mismatch between prediction and observation is known as the vacuum catastrophe, and it represents perhaps the single greatest embarrassment in all of theoretical physics. To grasp the sheer scale of this error, we need to venture into the bizarre world of quantum mechanics. According to our most successful theories, what we perceive as empty space is anything but. The vacuum is a hive of frenetic activity, a quantum foam where pairs of virtual particles, a particle and its antiparticle constantly pop into existence from nothing, borrowing energy from the universe for an unimaginably brief moment before annihilating each other and vanishing back into the void. This isn't just a speculative idea, it's a well-established phenomenon with real-world consequences, such as the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a slight push from the ghostly pressure of these virtual particles outside the plates. Every cubic centimeter of space, according to quantum field theory, is seething with this vacuum energy. The problem arises when we try to add up all of these tiny, fluctuating energy contributions to calculate the total energy density of empty space. The mathematics leads us to a number of almost incomprehensible size. This predicted vacuum energy should act exactly like Einstein's cosmological constant, exerting a powerful repulsive force. If this theoretical calculation were correct, the repulsive push of this energy would have been so immense in the early universe that it would have ripped apart every atom, star, and galaxy before they could even begin to form. The cosmos as we know it would have been torn to shreds in the first fractions of a second. The fact that we exist at all, that galaxies have had billions of years to coalesce, is proof that the actual vacuum energy density is not just a little bit smaller than the prediction. It is vanishingly, infinitesimally tiny by comparison. The observed value of dark energy is about 10 to the power of 120 times smaller than the theoretical prediction. That number is so vast it defies any everyday analogy. It's like predicting that an object weighs more than the entire observable universe, only to measure it and discover it weighs less than a single electron. This isn't a small rounding error. It's a signal that something is profoundly wrong with our understanding of the fundamental laws of nature. The vacuum catastrophe screams that our two most powerful and successful theories, quantum mechanics, which governs the incredibly small, and general relativity, which describes the immense scale of the cosmos, are fundamentally incompatible when they meet in the realm of empty space. This discrepancy suggests that either our understanding of the quantum vacuum is dangerously incomplete, or there is some mysterious yet unknown cancellation mechanism that almost perfectly, but not entirely, zeroes out this colossal vacuum energy, leaving behind the faint whisper we detect as dark energy. Solving this problem is considered the holy grail of modern physics, as it likely holds the key to a deeper, unified theory of everything. Given the profound difficulties with the cosmological constant, it's no surprise that physicists have been exploring alternative explanations for dark energy. One of the most compelling and elegant ideas is a concept known as quintessence. Unlike the static, unchanging energy density of the cosmological constant, quintessence proposes that dark energy is not a fixed property of the vacuum, but rather a dynamic, evolving force field that permeates all of space. The name itself is a nod to antiquity. In ancient philosophy, the quintessence was the fifth element, the pure and perfect substance that filled the heavens beyond the terrestrial realm of earth, air, fire, and water. In modern cosmology, it represents a similarly fundamental component, a new kind of field whose subtle variations over cosmic time could solve some of the biggest puzzles left by the standard model. The key difference lies in its behavior over time. Imagine the cosmological constant as a feature permanently etched into the fabric of space-time, like a spring built into the floor of the universe that exerts a constant, unwavering push. Quintessence, on the other hand, is more like a weather system moving through space. Its energy density can decrease or increase as the universe evolves. In some models, it acts as a fluid with a negative pressure, but one that can change its characteristics. This dynamism offers a potential solution to what is known as the cosmic coincidence problem. Why is it that we happen to live at the precise moment in cosmic history when the density of dark energy and the density of matter are roughly comparable? For nearly the universe's entire 14 billion-year history, matter was far more dominant. Dark energy's repulsive effect only overcame gravity's pull and started accelerating the expansion about 5 billion years ago. If dark energy is a fixed cosmological constant, this recent dominance is just a bizarre coincidence. We are here at the one special time when the two major cosmic components are in balance. Quintessence provides a way out of this conundrum. If the energy field evolves, it's possible that its rise to dominance was a natural consequence of its changing nature, not a random accident of timing. It could have been negligible in the early universe, allowing galaxies to form unhindered, and only later grew in influence to become the dominant force we observe today. The theoretical implications of quintessence are profound because it often requires the existence of a new fundamental particle, sometimes called a quintessarion. This particle would be the quantum manifestation of the field, much like the Higgs boson is for the Higgs field. Finding evidence for such a field would not only explain dark energy, but would also represent a monumental expansion of the standard model of particle physics. However, detecting quintessence is an even more formidable challenge than detecting dark matter. Since its effects are only noticeable on the largest possible scales, across billions of light years, we cannot build an experiment on Earth to probe it directly. The only way to test for it is through incredibly precise observations of the cosmos itself. Astronomers look for tiny deviations in the expansion history of the universe, searching for any sign that the strength of dark energy has changed over billions of years. They use the same tools that discover dark energy distant supernova, the large-scale structure of galaxies, and the faint imprint of sound waves frozen into the cosmic microwave background. But they analyze the data with a much finer tooth comb, seeking evidence that the acceleration rate is not constant, but is itself slowly accelerating or decelerating. So far, the data from these observations consistently agrees with a simple cosmological constant. The expansion appears to be accelerating at a steady rate. Yet, the measurements still have margins of error, and the possibility of a very slowly evolving quintessence field has not been completely ruled out. Future missions like the European Space Agency's Euclid Telescope and the Vera C. Rubin Observatory in Chile are designed to map the geometry of the universe with unprecedented precision. They will measure the distances to billions of galaxies, constructing a three-dimensional map of the cosmos that could reveal minute variations in the expansion rate across different epochs. If quintessence is real, these next-generation observatories might finally detect its subtle fingerprint, revealing a universe where the dark energy is not a monolithic constant, but a dynamic character in the evolving story of the cosmos. The hunt for quintessence is a testament to scientific ingenuity, a search for a ghostly field by measuring the stretching of spacetime itself across the entirety of cosmic history. This relentless acceleration, driven by the mysterious push of dark energy, doesn't just rewrite the history of our cosmos, it scripts its ultimate, chilling finale. For centuries, philosophers and scientists have pondered the fate of the universe, but it's only with the discovery of dark energy that we've been able to move from speculation to a scientifically grounded and profoundly sobering prediction. If dark energy is indeed a true cosmological constant, an unchanging force inherent to space itself, then the expansion we see today is not a temporary phase, it is the universe's permanent trajectory. This leads inexorably to a scenario known as the heat death, or more poetically, the Big Freeze. It is a fate not of fire and fury, but of ice and isolation, playing out on a timescale that dwarfs every epoch that has come before. To understand this distant future, we first need to consider the concept of the observable universe. Because the speed of light is finite, there is a fundamental limit to how far we can see. Every second, light from galaxies that are currently beyond that limit is finally reaching us, expanding our cosmic horizon. But dark energy introduces a sinister twist. As the expansion of space accelerates, there will come a point where galaxies that are currently speeding away from us will reach a velocity greater than the speed of light relative to our position. This isn't a violation of Einstein's laws. Nothing is moving through space faster than light. Rather, the space between us and those galaxies is itself stretching at an ever-increasing rate. When this happens, the light leaving those distant galaxies will simply never be able to make headway against the expanding void. It will be like a swimmer trying to cross a river that is widening faster than they can swim. Over trillions of years, this process will create a profound and growing isolation. Galaxy by galaxy, the lights in the cosmic sky will wink out, not because the stars within them have died, but because their light can no longer bridge the ever-widening gulf. Our local group of galaxies, bound together by gravity, will remain as a single, isolated island universe, but everything beyond it will have vanished from our view, receding into an impenetrable darkness. The universe will become a collection of disconnected galactic islands, each alone in an endless, expanding blackness, utterly unaware of the other's existence. Within these isolated islands, the second act of the cosmic tragedy will unfold. The raw material for new stars, the vast clouds of gas and dust that populate galaxies, will gradually be consumed. As the existing stars burn through their nuclear fuel, they will meet their own ends. Massive stars will explode as supernova, while smaller stars like our Sun will swell into red giants before collapsing into faint white dwarfs. But after these final fireworks, no new stars will ignite. The galaxy's stellar population will age and dim. The brilliant blue-white light of youthful stars will be replaced by the dull red glow of aging red dwarfs, the longest-lived stars in the universe. But even these faint embers will eventually flicker out. After quadrillions of years, the last star will die, and the universe will be plunged into a permanent twilight, lit only by the residual heat of dead stellar remnants, white dwarfs that slowly cool into black dwarfs, neutron stars, and black holes. The final stage is one of almost unimaginable stillness and decay. Over timescales so vast they make the current age of the universe seem like a single heartbeat. Even the fundamental structures of matter may not be safe. Some theoretical models suggest that over googolls of years, that's a 1 followed by 100 zeros, protons themselves, the building blocks of atomic nuclei, might decay. If this occurs, every single atom in the universe, every piece of what was once a star, a planet, or even a living being, will gradually evaporate into a faint drizzle of subatomic particles and radiation. Black holes, the last bastions of structure, will not last forever either. Through a quantum mechanical process known as Hawking radiation, they will slowly leak their mass away, eventually vanishing in a final, fleeting burst of energy. The universe will then be a truly cold, dark, and nearly empty void, a thin, ever-expanding soup of photons and elementary particles, so spread out that interactions between them become vanishingly rare. The temperature will approach absolute zero, and all organized energy will have been diluted away. This is the heat death, not an explosion, but an irreversible descent into equilibrium, a state of maximum entropy where no work can be done, no structure can form, and no meaningful change will ever occur again. It is a finale of perfect, eternal silence. While the Big Freeze presents a future of gradual dimming and isolation, there exists a far more violent and dramatic alternative, a cosmic doomsday scenario that hinges on a crucial property of dark energy we have yet to measure with certainty. What if the repulsive force driving the acceleration is not constant, but is actually growing stronger over time? This possibility opens the door to an end not of silence, but of cataclysm known as the Big Rip. Instead of a slow fading, this model predicts a definitive, finite moment in the future when the very fabric of space-time is torn asunder. The key to this terrifying fate lies in the equation of state of dark energy, a parameter physicists call W. This value describes the relationship between the energy density of dark energy and the pressure it exerts. For Einstein's cosmological constant, this value is fixed at exactly -1. This specific value produces a constant, unwavering acceleration. But if dark energy is something more dynamic, like quintessence, This W value could be less than -1, meaning the repulsive pressure is not just constant, but actually intensifying as the universe expands. Think of the difference between a steady, gentle breeze and a wind that grows into a hurricane. In the Big Rip scenario, dark energy is that hurricane, its force building relentlessly. The sequence of destruction would be as methodical as it is horrifying. It would not happen all at once, but in a cascading series of catastrophes, each more fundamental than the last. The first structures to go would be the largest gravitational-bound systems. About 60 million years before the end, the accelerating expansion would become so powerful that it would overcome the gravitational glue holding galaxy clusters together. These immense cities of galaxies would be ripped apart, their individual member galaxies flung into the ever-widening void. Then, as the end draws nearer, perhaps just months before the final moment, the same fate would befall individual galaxies. The gravitational bonds holding stars together in spiral arms and elliptical swarms would be severed. Our own Milky Way would be shredded, its stars becoming isolated orphans in the darkness. The destruction would then move inward, months would turn to minutes. With just minutes to spare, the expansion force would exceed the gravitational binding energy of our solar system. Planets would be torn from their orbits around the Sun, each sent careering off on its own solitary path through nothingness. The Earth would be ripped away from the Sun, its orbit unraveling in an instant. But the horror would not stop there. In the final fleeting moments, the force would become greater than the forces that hold matter itself together. With only seconds left, the expansion of space itself within our planet would overcome the electromagnetic forces that bind atoms into molecules and solids. The Earth and every object on it would be explosively disassembled, and in the last inconceivable fraction of a second, the same fate would meet atomic nuclei. The strong nuclear force, the most powerful force in nature that binds protons and neutrons together, would be vanquished. Every atom in the universe would be torn apart in a final, instantaneous flash. The entire observable universe would be reduced to a dilute, disconnected soup of fundamental particles and radiation, unable to ever interact again. The Big Rip is not a slow fading. It is a definitive, violent end to all structure, from the largest galaxy superclusters down to the very building blocks of reality. The question, then, is how we can possibly know which future awaits us. The answer lies in making the most precise measurements imaginable of the universe's expansion history. Astronomers are using tools like distant supernova, baryon acoustic oscillations frozen into the large-scale structure of galaxies, and the subtle imprints in the cosmic microwave background to measure the value of W with ever-increasing precision. Is it exactly -1, sealing our fate as a slow freeze, or is it something less, pointing toward an eventual rip? So far, all observations are consistent with a cosmological constant, a steady W of -1. But the error bars on our measurements, while shrinking, have not yet completely ruled out the more dramatic possibility. Future missions like the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory are designed to measure the expansion history with such exquisite detail that they could detect even a tiny deviation from -1. The search for our ultimate fate is therefore a race of measurement against theory, a quest to pin down the true nature of the dark energy that holds the destiny of everything in its grasp. But to chart the future of the cosmos, we need a map of its past, a way to measure distances across billions of years with incredible accuracy. This is where one of the most elegant tools in cosmology comes into play, a fossilized echo from the dawn of time known as baryon acoustic oscillations. The name sounds complex, but the concept is a beautiful blend of simple physics and cosmic scale, providing us with a fixed measuring stick etched into the very fabric of the universe. To understand how it works, we need to journey back once more to the universe's first few 100,000 years, to that hot, dense plasma of particles and light we encountered earlier. In that primordial soup, gravity was trying to pull matter together, while the intense pressure of radiation was pushing it apart. This created a tug of war that set the entire universe ringing like a bell. Regions of slightly higher density would collapse inward under their own gravity, but as they compressed, the radiation pressure inside would build up, eventually becoming so strong that it would blast the material outward in a spherical wave. This cycle would then repeat. The result was a universe filled with propagating sound waves, ripples moving through the particle soup at a significant fraction of the speed of light. These waves traveled outward until a critical moment when the universe cooled enough for atoms to form, an event called recombination. At that instant, the photons suddenly decoupled from the matter, flying free to become the cosmic microwave background we observe today. Without the radiation pressure to push back, the sound waves simply stopped in their tracks, freezing the ripples in place. What was left behind was a subtle but permanent pattern. Each of those original overdense regions became surrounded by a spherical shell of matter, a cosmic echo of that final sound wave. The size of this shell is determined by the distance the sound wave could travel in the roughly 400,000 years before recombination. This distance became a fixed scale, a standard ruler imprinted on the universe. Today, that same scale is visible in the way galaxies are distributed across the sky. When astronomers create three-dimensional maps of millions of galaxies, they don't see a perfectly random distribution. They find that galaxies are slightly more likely to be separated by a specific distance, about 500 million light-years, than by any other. This preferred separation is the modern-day signature of those ancient sound waves, the ghostly imprint of that spherical shell from the early universe. It is the Baryan acoustic oscillation scale, and it is the same everywhere, providing a consistent measuring stick that is independent of a galaxy's brightness or age. This is the true power of the BAO technique. By looking at galaxy maps from different eras, by observing the universe when it was, say, 8 billion years old versus its current age of nearly 14 billion years, astronomers can measure the apparent size of this standard ruler at those different times. Because the universe is expanding, the ruler will appear to have a larger angular size when we look back to earlier epochs when the universe was smaller. It works just like any object viewed from a distance. The farther away it is, the smaller it appears. By precisely measuring how the apparent size of this 500 million light-year ruler changes over cosmic time, scientists can plot exactly how the universe has expanded throughout its history. This gives us a direct and incredibly robust way to measure the effect of dark energy. If the expansion were decelerating, the change in the ruler's apparent size would follow one curve. The discovery that it follows a different curve, one that shows the expansion starting to accelerate around 5 billion years ago, is a powerful, independent confirmation of dark energy's dominant role. Baryan acoustic oscillations act as a cosmic dipstick, allowing us to gauge the expansion rate of the universe across billions of years with a level of precision that helps to cross-check and reinforce the evidence from supernova, creating a multi-pronged and undeniable case for the accelerating cosmos. But to truly understand the cosmic recipe, the precise proportions of dark matter, dark energy, and the ordinary stuff we're made of, we need the most pristine snapshot of the infant universe ever taken. This brings us to the cosmic microwave background, or CMB, the oldest light in existence. It is the afterglow of the Big Bang itself, a fossilized echo from a time when the universe was just 380,000 years old, a mere infant compared to its current age of nearly 14 billion years. Before this moment, the cosmos was an opaque, searing hot plasma, a dense fog of protons, electrons, and light. Photons couldn't travel more than a tiny distance before bouncing off a free electron, like light trying to shine through thick, swirling smoke. But as the universe expanded and cooled, it eventually reached a temperature where electrons could combine with protons to form the first neutral atoms. In that instant, the fog lifted. The photons, suddenly freed from their constant collisions, were released to travel across the universe in a straight line. That first flash of light, now stretched and cooled by the subsequent expansion of space over billions of years, reaches us today not as visible light, but as a faint microwave signal that uniformly bathes the entire sky. It is the baby picture of the cosmos. However, this baby picture is not perfectly smooth. It contains tiny, crucial imperfections, minute variations in temperature, warmer spots and cooler spots that differ by only a few millionths of a degree. These fluctuations are the blueprints for everything that would follow. They represent the seeds of all future structure, the slight overdensities and underdensities in the primordial soup. It was within these slightly denser regions that dark matter's gravitational pull began to work, attracting more matter and eventually leading to the formation of galaxies and clusters. The specific pattern of these hot and cold spots, their size and distribution across the sky, is not random. It holds encoded within it the fundamental parameters of the universe, a cosmic fingerprint that reveals its exact composition and geometry. This is where missions like the European Space Agency's Planck satellite come in. Planck was an extraordinarily sensitive observatory designed to map the CMB with unprecedented precision, measuring its temperature variations across the entire sky. By analyzing the statistical properties of these fluctuations, essentially, by measuring how likely spots of a certain size are to appear, cosmologists can perform a kind of cosmic autopsy. The most prominent feature in this pattern is related to the size of the universe at the moment the CMB was released, which is determined by how far sound waves could travel in the plasma before atoms formed. This scale, known as the sound horizon, appears as a preferred size for the hot and cold spots in the Planck data. The observed angular size of this standard ruler on the sky today tells us directly about the geometry of the universe. If the universe were flat, like a sheet of paper, the spots would appear at a certain size. A positively curved universe would make them look larger, while a negatively curved one would make them appear smaller. The Planck data confirms with stunning certainty that the universe is geometrically flat too, within a tiny margin of error. This finding of flatness has a profound implication rooted in Einstein's theory of general relativity. The total energy density of the universe must be exactly equal to a specific critical value. It's like a cosmic balancing act. The CMB measurements allow us to precisely weigh the different components that contribute to this total density. The patterns of the fluctuations are exquisitely sensitive to the amounts of normal matter, dark matter, and the influence of dark energy. For instance, the relative heights of the peaks in the fluctuation spectrum tell us about the struggle between gravity and pressure in the early universe. The amount of normal matter which interacts with light affects how the sound waves propagated. The amount of dark matter which only feels gravity governs how the gravitational potential wells evolved. And the overall geometry, confirmed by the size of the first peak, pins down the total density which, when you subtract the matter components, leaves the remainder as dark energy. The results from Planck and other experiments are nothing short of breathtaking in their precision. They tell us that normal matter, all the stars, planets, gas, and dust, makes up just 4.9% of the universe. Dark matter, the invisible scaffolding, accounts for 26.8%. And dark energy, the mysterious force driving the acceleration, constitutes a dominant 68.3%. These numbers are not rough estimates. They are known with an accuracy of better than 1%. It is a humbling and definitive inventory of reality, revealing that the world of atoms and light we have spent centuries studying is a mere sprinkling on a cosmic ocean dominated by invisible, enigmatic forces. The cosmic microwave background is our Rosetta Stone, and we have finally learned to read its message, a message that tells us exactly what the universe is made of, even as we struggle to understand what those ingredients truly are. Now, having explored these two cosmic giants individually, it's time to bring them face to face. The story of our universe, from its fiery birth to its ultimate fate, is fundamentally a tale of a great cosmic tug of war, a battle between two opposing forces we cannot see. On one side, we have dark matter, the great cosmic architect. Its role is defined by gravity, the force of attraction. It works tirelessly to pull matter together, to build structure, to assemble galaxies and weave the immense cosmic web that gives the universe its rich texture. Dark matter is the ultimate gatherer, the force of construction and consolidation. On the other side stands dark energy, the great cosmic repulsor. Its role is one of expansion, of pushing the very fabric of space itself apart. It is the force of dispersal, working to dilute the universe, to separate galaxies, and to overwhelm the cohesive power of gravity. Dark matter builds up, dark energy tears down. This fundamental opposition is the central drama of modern cosmology. To understand how this drama has unfolded, we need to look at the history of the universe as a whole. For nearly 9 billion years after the Big Bang, the cosmos was a much smaller, denser place. In this environment, dark matter was the undisputed champion. Its gravitational pull was the dominant influence. It sculpted the first structures, gathered the primordial gas, and oversaw the birth of galaxies and clusters. The expansion of the universe, set in motion by the Big Bang, was steadily slowing down under the collective gravitational brake applied by all this matter, both dark and normal. It was a universe under construction where gravity was firmly in control of the cosmic agenda. But then, around 5 billion years ago, a profound shift occurred, a cosmic changing of the guard. As the universe continued to expand, the density of matter, both dark and normal, was steadily decreasing. Matter becomes more dilute as space grows. Dark energy, however, if it truly is a property of space itself, as the cosmological constant suggests, behaves differently. Its energy density remains constant. Imagine a checkerboard that is constantly growing in size. The number of checkers on the board representing matter stays the same, so they become more spread out. But the dark energy is like a property of each individual square on the board. As you add more squares, the total amount of dark energy increases. So, while matter's influence weakens with expansion, dark energy's influence grows stronger. About 5 billion years ago, the scales finally tipped. The density of matter dropped to a point where it was surpassed by the relentless, unchanging push of dark energy. From that moment on, the expansion of the universe stopped slowing down and began to accelerate. Think of it like a ball thrown vertically into the air. For the first part of its journey, gravity is pulling it down, slowing its ascent. This is the era of dark matter dominance. But if that ball had a tiny rocket attached to it that provided a constant upward thrust, there would come a point where the rocket's push would overcome the pull of gravity. The ball would then not only continue to rise, but would begin to speed up as it climbed higher. The rocket is dark energy, and that transition point 5 billion years ago was when the acceleration began. It is a staggering thought that this cosmic takeover coincided roughly with the formation of our own solar system and our planet Earth. We emerged at a pivotal moment in cosmic history, just as the universe's dominant force was shifting from one of attraction to one of repulsion. This ongoing battle has profound implications for the future we discussed earlier. If dark energy continues to dominate, the fate of the universe is the Big Freeze, a future of increasing isolation and darkness. But this cosmic struggle also leaves its mark on the present. We can see its evidence in the way galaxy clusters are being pulled apart by the expanding flow of space, their gravitational bonds straining against the relentless push. The universe is now a construction site where the foreman, dark matter, is still trying to build, but the site itself is being constantly and rapidly enlarged by dark energy, making it harder and harder to complete any new large-scale structures. The tug-of-war is over for now. Dark energy has won the dominant role, but its opponent, dark matter, remains a powerful presence, its gravitational handiwork etched permanently into the cosmic landscape, even as that landscape is stretched toward an ever more distant horizon. Given their opposite roles in the cosmos, one pulling things together, the other pushing them apart, dark matter and dark energy appear to be fundamental adversaries in the great cosmic struggle. But what if this opposition is merely an illusion? What if these two dominant yet mysterious components of the universe are not separate entities at all, but are instead two different faces of a single, unified substance whose behavior changes over cosmic time? This idea, while highly speculative, represents one of the most ambitious frontiers in theoretical cosmology, an attempt to solve the two greatest mysteries of the universe with one elegant, sweeping concept. Imagine discovering that two seemingly different forces, like electricity and magnetism, were actually intertwined manifestations of a single electromagnetic force. A unified theory for the dark sector would represent a similar, monumental leap in our understanding. One of the most well-known proposals in this direction is the concept of a Chaplygin gas. This isn't a gas in the ordinary sense like steam or oxygen, but a theoretical fluid with a truly bizarre property. In the early, dense universe, this exotic substance would have behaved just like dark matter. Its particles would have clumped together under gravity, providing the gravitational scaffolding necessary for galaxies to form. It would have been essentially cold and pressureless, acting as the universe's prime architect. But as the universe expanded and became more diffuse, the nature of this Chaplygin gas would have undergone a profound metamorphosis. Its internal pressure would have changed, transforming it from a clumping, attractive fluid into a smooth, pervasive energy with a strong negative pressure, a substance that drives the expansion of space apart. In this model, the same underlying dark stuff is responsible for both structure formation and the accelerated expansion, simply expressing different aspects of its nature as the cosmic environment evolves. It's a compelling idea, a single chameleonic entity that first builds the cosmic web and then dictates its ultimate fate. While the Chaplygin gas is a specific proposal, the broader idea of unification has spawned other fascinating models. Some theories suggest the existence of a single quantum field that permeates all of space, much like the Higgs field, but one that can fluctuate in such a way that it sometimes acts as a source of gravity like matter, and at other times as a source of repulsion like dark energy. The behavior of this field would be tied to the density of the universe. When matter is densely packed in the early cosmos, the field gets trapped in a state that makes it act like collisionless particles. But as the universe expands and empties out, the field can roll into a new configuration where its dominant characteristic is a constant energy density, effectively becoming the cosmological constant. This elegantly addresses the cosmic coincidence problem, the puzzling observation that we live at the special time when dark matter and dark energy densities are comparable. In a unified model, this isn't a coincidence at all. It's simply a natural phase transition in the evolution of the single dark component. However, for all their theoretical elegance, these unified models face significant challenges when confronted with real-world observations. The primary hurdle is that dark matter and dark energy, as we observe them, appear to behave very differently. The evidence from collisions like the bullet cluster strongly suggests that dark matter is collisionless. It can pass through itself and other matter without slowing down. A unified fluid, on the other hand, would likely have some internal friction or sound waves that would affect how it clumps, potentially leaving a different imprint on the large-scale structure of the universe than what we actually see. Furthermore, the precise measurements of the cosmic microwave background from the Planck satellite have placed very tight constraints on the properties of dark matter. The observed patterns of temperature fluctuations are exquisitely sensitive to the timing of when structures form, and so far, the data fits the standard model of cold, collisionless dark matter remarkably well. While some unified models can be tweaked to fit the data, they often lose the very simplicity that made them attractive in the first place, becoming more complex than the two-component model they seek to replace. The quest to unify the dark sector is a high-stakes endeavor. If successful, it would represent a simplification of our cosmic inventory, a profound Occam's razor moment that reveals a deeper layer of reality beneath the two great mysteries. It would imply that we have been studying two different symptoms of the same underlying cause. Yet, the current lack of conclusive evidence for such models reminds us that nature is under no obligation to conform to our desire for elegant simplicity. The universe may indeed be built upon a more complex foundation, where dark matter and dark energy are genuinely distinct phenomena, each requiring its own unique explanation. This ongoing tension between the drive for unification and the stubbornness of observational data is the very engine of scientific progress, pushing theorists to refine their ideas and observers to sharpen their measurements in the hope of one day glimpsing a unified truth behind the cosmic shadows. Yet for all the stunning precision of our cosmic inventory, a troubling crack has begun to appear in the very foundation of modern cosmology, a discrepancy so persistent that it threatens to unravel our carefully constructed picture of the universe. This crack is known as the Hubble tension, and it centers on a single, fundamental number, the Hubble constant. This value represents the current rate of the universe's expansion, the speed at which galaxies are receding from us at this very moment. You might think that measuring such a crucial parameter would yield a single, agreed-upon answer, but that is far from the case. Instead, we have two separate, incredibly precise methods for measuring this rate, and they are stubbornly disagreeing with one another. It's as if you used two different, highly accurate rulers to measure the same table and got two different lengths that are undeniably, definitively not the same. This isn't a small margin of error. It is a glaring inconsistency that points toward something missing from our equations, something potentially revolutionary. The first method looks at the universe in its adolescence, using the cosmic microwave background as our ultimate benchmark. The Planck satellite's map of the infant universe is so detailed that it allows cosmologists to run the cosmic film backwards. They can take the initial conditions imprinted on the CMB, the exact pattern of density fluctuations, and use our standard model of cosmology, known as lambda CDM for lambda, or dark energy, and cold dark matter, to simulate 14 billion years of cosmic evolution. This simulation predicts how fast the universe should be expanding today. It's a top-down approach, starting with the baby picture and predicting the adult. The result from this method is a Hubble constant of about 67 kilometers per second per megaparsec. This means that for every megaparsec, a distance of about 3.3 million light-years, a galaxy is away from us, its recessional velocity increases by 67 kilometers per second. The second method takes a bottom-up approach, measuring the expansion rate directly in our local, modern universe. This is the legacy of Edwin Hubble himself, using a cosmic distance ladder to gauge how far away nearby galaxies are and how fast they are moving. The first rung of this ladder involves incredibly reliable cosmic yardsticks like Cepheid variable stars. These are stars that pulsate with a regularity directly tied to their true intrinsic brightness. By measuring their pulsation period, astronomers know exactly how bright they should be. Comparing this known brightness to how dim they appear in the sky tells us their distance with remarkable accuracy. By observing Cepheids in galaxies relatively close to us, we can calibrate even brighter standard candles like Type Ia supernova, which can then be seen at much greater distances. When you combine these precise distance measurements with the redshift of the galaxies, how much their light has been stretched by the expansion of space, you get a direct local measurement of the Hubble constant. And this is where the tension arises. This local measurement consistently gives a faster expansion rate, around 73 kilometers per second per megaparsec. A difference of 6 kilometers per second might not sound like much, but the uncertainty in both measurements has shrunk to such a degree that the gap is now highly significant, at a level of about 5 sigma. In scientific terms, this means there is only a 1 in a million chance that this discrepancy is a random fluke. The two most precise ways we have of measuring the universe's expansion are fundamentally at odds. If our standard cosmological model were perfect, the early universe prediction and the local measurement should agree perfectly. The fact that they do not suggests that the model, while incredibly successful, might be incomplete. This tension is not a minor detail. It is a potential chink in the armor of our understanding, a hint that there is something about the universe's evolution that we have not yet accounted for. So, what could be causing this discrepancy? The most exciting possibility is that it points toward new physics, a phenomenon beyond our current model of dark energy and dark matter. Perhaps dark energy is not a simple cosmological constant after all. Maybe its strength has increased over time, causing the expansion to accelerate more quickly in the recent past than our models assume. This would make the local universe appear to be expanding faster than predicted from the early universe's initial conditions. Another idea involves an early, brief phase of early dark energy, a new form of energy field that existed only for a short time in the very early universe, subtly altering the sound horizon scale imprinted on the CMB and thereby changing the prediction for today's expansion rate. Other proposals suggest modifications to gravity itself, or the existence of previously unknown types of neutrinos that interacted with matter and radiation in the primordial plasma. The Hubble tension has become a fertile ground for theoretical innovation, forcing physicists to think creatively about what might be missing from our cosmic recipe. It serves as a powerful reminder that our understanding of the universe is not a finished book, but a living document, constantly being revised and rewritten in the face of new and puzzling evidence. Faced with such a profound puzzle as the Hubble tension, we cannot rely on theory alone. To crack the code of dark matter and dark energy, we need sharper eyes on the sky, instruments of unprecedented power designed to probe the cosmos with a clarity we've only dreamed of. This is not a distant future aspiration. We are entering a golden age of observational cosmology, a new era defined by a fleet of next-generation observatories that will transform our view of the dark universe. These are not merely incremental improvements, they are quantum leaps in capability, each designed to attack the mystery from a different angle, and together they promise to rewrite our textbooks. Leading this charge is the James Webb Space Telescope, a name already famous for its stunning images of the early universe. But beyond the breathtaking beauty, Webb's scientific mission is deeply connected to our dark cosmic story. Its unparalleled infrared vision allows it to peer back in time to see the very first galaxies as they were forming. By studying these infant galaxies, astronomers can test our understanding of how dark matter's gravitational scaffolding guided their birth and growth. Do these primordial structures match the predictions of our lambda CDM model? Or do they show subtle differences that could point to new properties of dark matter, perhaps revealing that it interacts with itself or decays over time? Webb acts as a cosmic archaeologist, digging into the universe's deepest past to see if the foundations laid by dark matter are exactly as we believe, providing crucial tests that ground truth our models of cosmic evolution. While Webb looks deep into specific patches of sky, the next wave of observatories will take the opposite approach, casting an incredibly wide net. The Nancy Grace Roman Space Telescope, set to launch later this decade, is designed for a monumental task: cosmic cartography on a grand scale. Imagine Webb as a powerful telephoto lens capturing exquisite detail on a single subject. Roman will be a wide-angle lens of astonishing power, capable of capturing a swath of sky 100 times larger than Hubble's detailed view in a single snapshot. Its primary mission is to investigate dark energy through three powerful techniques simultaneously. It will discover and measure thousands of distant Type Ia supernova, building a much more precise history of the universe's expansion. It will map the distribution of millions of galaxies to measure baryon acoustic oscillations with exquisite detail across a vast volume of space. And it will study the subtle distortions in the shapes of galaxies caused by gravitational lensing, creating the most detailed map yet of the dark matter web that permeates the cosmos. By combining these probes, Roman will measure the properties of dark energy with a precision that could finally determine if it is a simple cosmological constant or something more dynamic like quintessence. On the ground, complementing these space-based giants, is the Vera C. Rubin Observatory in Chile. Its mission is one of pure, relentless observation. Its cornerstone is the Legacy Survey of Space and Time, or LSST, a 10-year project that will scan the entire southern sky every few nights. This is not a static map, but a dynamic movie of the cosmos. The LSST will detect billions of galaxies and track changes in their brightness and position over time. This torrent of data, amounting to over 20 terabytes every night, will be a treasure trove for dark energy science. It will allow for the most precise measurement of the weak gravitational lensing effect, revealing the distribution of dark matter in unprecedented detail. It will also find so many distant supernova that our map of the expansion history will become exquisitely refined. But perhaps most excitingly, the survey's sheer volume and repeated observations are a recipe for discovery. By constantly monitoring the sky, the Rubin Observatory is perfectly poised to find the unexpected anomalies or new phenomena that don't fit our current models. It is through such surprises that the most profound breakthroughs often occur. The true power of this new astronomical toolkit, however, lies not in any single instrument but in their synergy. Imagine Webb identifying a peculiar, ancient galaxy that challenges our models of structure formation. Roman could then place that galaxy in the context of a vast cosmic neighborhood, mapping the dark matter halo it resides within. Simultaneously, Rubin would be monitoring that entire region of the sky for any temporal changes, any flickers or shifts that might hint at dynamic dark matter interactions. This multi-messenger, multi-wavelength approach creates a feedback loop of discovery, where observations from one telescope inform and refine the questions being asked by the others. We are no longer just taking a snapshot of the universe. We are building a high-definition, multi-dimensional movie of its evolution, with dark matter and dark energy as the lead characters. The data collected over the next decade will provide the essential clues needed to solve the Hubble tension, to determine the true nature of dark energy, and perhaps even to make the first direct detection of the dark matter particle. We are on the cusp of a revolution, and these magnificent machines are our keys to the dark. This journey through the shadows of the cosmos leads us to a final, and perhaps the most profound fact of all. Beyond the intricate equations, the colossal experiments, and the mind-bending theories lies a simple, humbling truth that redefines our very place in reality. The revelation that 95% of the universe is composed of entities we cannot see, do not understand, and were completely unaware of until a cosmic eye blink ago, is not just a scientific finding, it is a monumental philosophical earthquake. For centuries, humanity has looked to the stars and believed that by studying the light, we were studying the universe. We constructed our laws of physics based on the behavior of the atoms that make up our world, confident that these rules governed everything. We saw ourselves as the pinnacle of a cosmic order we were on the verge of comprehending. The discoveries of dark matter and dark energy have shattered that confidence in the most beautiful way possible. They have delivered a powerful lesson in humility, reminding us that our perception of reality is not just limited, but is fundamentally blind to the true nature of existence. This humbling extends to the very foundations of our knowledge. For generations, physics has been built on the bedrock of the scientific method. Observe, hypothesize, test, and conclude. This process has given us incredible power, from splitting the atom to landing on the moon. We began to believe we were writing the rulebook for the cosmos. But dark matter and dark energy are a stark declaration that the universe has been playing by a different set of rules all along, and we have only just noticed. Our most successful theory, the Standard Model of particle physics, brilliantly explains the 5% of the universe we call normal matter. Yet it is utterly silent on the 95% that actually governs the cosmos's fate. This isn't a small gap to be filled in. It is a chasm that reveals our current understanding is a tiny island in a vast ocean of ignorance. We are like explorers who have meticulously mapped a single coastline, only to recently discover that an entire continent lies beyond the horizon, operating under principles we have yet to imagine. This shift in perspective forces us to reconsider what we mean by reality. We experience a world of solidity, of light and matter, of cause and effect. But this experience is a facade, a user interface generated by our biological senses that evolved to help us survive on Earth. Dark matter and dark energy show us that the true underlying reality is something far more strange and wondrous. The vast majority of the universe is composed of substances that do not interact with light, that might not even be made of particles as we know them, and that exert forces which defy our everyday intuition. The solid chair you are sitting on is, at its core, mostly empty space, and it is continuously being passed through by a wind of invisible matter, while the space it occupies is being stretched apart by a repulsive energy. The world we perceive is a delicate shimmer on the surface of a deep, dark, and fundamentally alien ocean. Perhaps the most inspiring aspect of this humbling reality is what it says about the future of discovery. The existence of these profound mysteries is not a failure of science, it is its greatest triumph. It is a sign that we have finally asked the right questions, that our tools have become sharp enough to reveal the boundaries of our knowledge. Every great revolution in human thought, from realizing the Earth revolves around the Sun to understanding that space and time are relative, began with a similar moment of humbling discontinuity. The discomfort of not knowing is the engine of progress. The mystery of the dark universe is an open invitation, a challenge to the next generation of thinkers to look beyond the visible, to question the fundamental assumptions we hold dear, and to conceive of a physics that is grander and more magnificent than anything we have yet dreamed. In acknowledging our ignorance, we open the door to a deeper, more meaningful understanding of the cosmos and our small, but uniquely curious place within it. And so we arrive at the final, and perhaps most profound fact of all. After exploring these 24 incredible truths about dark matter and dark energy, from their ghostly gravitational effects to their control over the universe's ultimate fate, one overarching reality comes into sharp focus. The quest to understand the dark universe is far more than an abstract puzzle for astronomers and physicists to solve in their ivory towers. It is a fundamental human endeavor that strikes at the very core of our existence, a journey to answer the oldest and most profound questions we have ever asked. What is the universe truly made of? How did it all begin, and perhaps most hauntingly, how will it all end? For millennia, humanity has looked to the stars for answers, crafting myths and developing scientific theories to explain our place in the cosmos. Each major discovery, from Galileo's telescope revealing the moons of Jupiter to Hubble's revelation of the expanding universe, has dramatically reshaped our worldview. Yet, the discovery that 95% of reality is completely hidden from us represents the most radical shift in perspective yet. It tells us that the universe we experience with our senses is a mere facade, a shimmering surface on an ocean of darkness. Solving this mystery is not just about filling in a gap in a textbook, it is about completing our picture of reality itself. The answers we seek will not merely add a new chapter to physics. They will likely require us to rip out the old one and start anew, forging a revolution as profound as those sparked by Newton's laws or Einstein's theory of relativity. This impending revolution points toward the single biggest unsolved problem in all of theoretical physics, the unification of general relativity, which governs the immense scale of planets, stars, and galaxies with quantum mechanics, the rules that dictate the bizarre behavior of the subatomic world. These two pillars of modern physics are brilliantly successful in their respective domains, but they are fundamentally incompatible with one another. They speak different mathematical languages and describe a universe that seems to operate by two different sets of rules. Dark matter and dark energy are the glaring, universe-sized symptoms of this disconnect. The vacuum catastrophe, where our best quantum calculations of empty space's energy are wrong by a factor of 1 with 120 zeros, is a screaming signal that our theories are incomplete. It is as if we have two different keys, each perfectly able to open a separate lock, but we are presented with a door that requires both to be turned at once. The true nature of dark matter and dark energy is almost certainly hidden in the physics that will bridge this chasm. The particle that makes up dark matter, whether it is a WIMP, an action, or something entirely unforeseen, is not part of our standard model. Discovering it would immediately force an expansion of our understanding of the fundamental constituents of matter. Similarly, understanding whether dark energy is a simple cosmological constant, a dynamic field like quintessence, or something even more exotic, will require a theory that seamlessly blends the very large with the very small. The solution to the dark universe mystery is widely believed to be the very key that will unlock the door to a theory of everything, a single, coherent framework that can describe every force and every particle in the cosmos, from the birth of the universe in a quantum fluctuation to its ultimate fate billions of years from now. This is why the search matters so deeply. It is a quest that transcends academic curiosity. The technological spin-offs from this research alone are immense. The development of ultra-sensitive detectors for dark matter has pushed the boundaries of material science and quantum sensing. The algorithms created to analyze the cosmic microwave background or the data from the Vera C. Rubin Observatory drive innovation in computing and artificial intelligence. But beyond the practical applications, the pursuit answers a deep, innate human need to understand the world we live in. It is a story of humility, showing us how much we have yet to learn, and simultaneously a story of audacious ambition, as we strive to comprehend the entirety of existence. The mystery of the dark universe is the greatest story ever told, and we are living in the chapter where the protagonist scientists around the world are piecing together the plot. The final answers will not only reveal the hidden architecture of the cosmos, but will also redefine our species' place within it, marking a milestone in the intellectual evolution of humanity. So as we reach the end of our journey through the dark, let's take a moment to look back at the astonishing landscape we've traveled. We began with a universe of light, the stars and galaxies we can see, only to discover they are merely the glittering decorations on a far grander, invisible structure. We followed the ghostly fingerprints of dark matter, from Fritz Zwicky's observations of galaxy clusters flying apart to Vera Rubin's definitive proof of flat rotation curves, revealing an unseen gravitational hand that holds the cosmos together. We've witnessed how this dark matter acted as the cosmic architect, drawing up the blueprints for the vast web of galaxies in which we reside. And then we confronted the ultimate plot twist, the discovery that this expansion isn't slowing down, but is instead accelerating, propelled by the mysterious repulsive force of dark energy, a force so dominant it dictates the ultimate fate of everything. This journey forces a profound shift in perspective. We are not living in a universe made primarily of the atoms we know and love. We are inhabitants of a cosmos where 95% of reality is fundamentally foreign to us. The quest to understand this dark sector is more than just a scientific challenge. It is one of the greatest detective stories ever told, a puzzle whose solution will undoubtedly rewrite the textbooks of physics and reveal a deeper layer of reality. The excitement lies in the fact that we are living through the pivotal chapters of this story right now, with a new generation of incredible observatories like the James Webb Space Telescope, the Vera-C, Rubin Observatory, and the Nancy Grace Roman Space Telescope coming online. We are equipping ourselves with tools of unprecedented power to peer into the darkness. These instruments are not just bigger cameras, they are time machines and cosmic cartographers that will map the dark matter web, measure the history of expansion with razor-sharp precision, and perhaps even catch a glimpse of the dark matter particle itself. The mystery of the dark universe is an open invitation, a challenge to our curiosity and ingenuity. It's a reminder that the cosmos is far stranger and more wonderful than we ever imagined, and that the biggest discoveries often lie not in the answers we have, but in the questions we have only just learned to ask. We want to hear from you on this journey of discovery. After exploring these 25 mind-blowing facts, which one reshaped your understanding of the cosmos the most? Was it the sheer scale of our ignorance, the 5% figure, the bulletproof evidence from the bullet cluster, or the haunting future of the Big Freeze or the Big Rip? Let us know in the comments below which fact captivated you and what mysteries you'd like us to explore next. If you enjoyed this deep dive into the cosmic shadows, make sure to subscribe and hit the notification bell so you don't miss our next adventure to the frontiers of space and time. The universe is full of secrets waiting to be uncovered, and we're just getting started.